we need to define what is the architecture. And the real key point here is that the architecture is a specification. It's the specification that hardware provides to software, and it's really about the interface between both to try to hide as much nasty hardware details from software. And so ideally, the software can only think about the architecture and not about actual hardware. And for that property to be true, the architecture contains a bit more than what we would actually want it to contain. But more concretely, the goal is to define an envelope of allowed behavior that software can observe. And that is the only sane thing to do. So either we can think a bit about a set of final states that are reachable from a given initial state, or we can be a bit more precise about defining sets of allowed instruction traces or witnesses. So in order to define the architecture, one trick that we have tried to use is to split it in two parts. So the instruction set architecture model. So the instruction model is the usual architecture of pseudocode, so SAIL, ASL, or whatever. And in some sense, the goal is to cram as much as possible of the architecture complexity into that. But it's still not enough to get the whole architecture. And so what I globally call the concurrency model is what remains. So what you need to go from the pseudocode to an actual machine model. So that includes the memory model, as usual, but there is also a register model. So most people that do weak memory model assume that they get handed out address and data dependency out of magic. It's not the case, and we need to define those things properly. Then there are also relaxed register accesses. So all of this is inside a single thread, but there are a lot of complexity to manage here. And then there is all the system stuff, virtual memory, exception, instruction fetching, and devices. And as a remark here, a bit like Alistair Reed did last week about trying to push as much as possible of the architecture into a structured database instead of code at a lower level, pushing as much as possible into code and not axiomatic model with arrows or fiddly operational model is the best. So, I mean, right now I'm taking the SAIL as is and making up what's missing to reach a machine model, but later it would be nice if other things from the lower box could be moved back up in the upper box to be written as regular code. That would make our life simpler. So why this project? So the goal is to formalize in a prover the full model with the real ASA. So this is a bit of a table of, to my knowledge, the state of the art. So we have some tools, testing tools that can take litmus tests and tell you what are the allowed behavior. So there is Herd that currently works on a toy ASA, but they are working on making it work on actual ASL. And then there is Isla and Armem that currently work on actual SAIL. Armem a bit of an older version, but details. But in the prover world, like in proof assistance, so far, as far as I know, all the developments have used some kind of toy ASA. So for example, the promising proof of Popper 19 that proved an equivalence between a promising and an axiomatic ARM model just had a toy assembly with like 5 or 6 instructions as the baseline for that proof. Then there are other projects like IMM that define well the memory model, but by being totally abstract on what actually events are, like reads, write, and all that, which is good for proving equivalence between concurrency model, but does not really give us a model of the architecture. And so this work is trying to be the intersection of actually working with the real ISA model and inside the theorem prover. So why do we want this? So, I mean, there are many points, most of them obvious-ish, but still good to list them. So when we talk about CPUs, so for user modes, we can think it's mostly done, even if not really. But as we go towards system stuff or interaction with GPU, all those models get increasingly large and complex. And like just testers is not good enough. We need to start making proofs about them and have them in a prover formally defined from bottom to top. And all of these tools like Herd, Isla, Armem have lots of implicit semantics that are not obvious, that are definitely not written in the corresponding papers. And those hidden semantics are critical for the correct definition of the architecture. And it would be nice to get this formalized. And once we have this, we enable the whole arsenal of formal methods over formally defined semantics like refinement proof, program logic, model equivalence proof, all in a proof assistant checked way, which is really useful. And this will finally allow us to verify all the system bits of project like SEL4, SEKVM that makes either weird assumption about the concurrency model or no assumption at all. I mean, SEL4 just assume that their TLB interaction code is correct, period. So to do all of the things, we need such a model. So I'm trying to do that. So more precisely, I'm trying to do a reusable, hopefully, formal framework to define hardware models. So I mean, hardware is CPUs or possibly GPUs, but mostly I'm focusing on CPUs here. In a proof assistant in a way that is architecture generic. So you need to instantiate precisely for your architecture, but the baseline of the model is generic. Concurrency model generic, so you can plug in whatever style of concurrency model you want, axiomatic, promising, microarchitectural, including flat, pop, flowing, whatever. And on the other hand, I want it to be also instruction set architecture definition generic, so you can use SAIL, you can use ASL, you can use symbolically simplified version of those. And hopefully you can pick whatever on both sides, click them together, get a machine model, and it will work out. That's the theory. And last bit, we want all of this to be executable because right now, official models are often defined by tools. Like for example, the official R memory model is defined by the HER tool, and the only way you can compare whatever you're doing with the HER tool is being able to run the same test and checking you get the same results. So we really want all of this framework to allow us to write model that then you can actually run at least on small tests. So the main point here is that to define this machine model, we need to combine both the instruction model and the concurrency model in a sane and reusable way. And so a big part of this project is defining an interface, both a generic one and a specific architecture instantiation of that interface. So sadly, this interface can't be fully generic, but it's mostly generic with small holes where you can put architecture-specific stuff. And we try to keep that interface as small as possible so you can reason about one side without thinking too much about the other one, and you can still at the end compose them and get a full machine model. So what the interface looks like, so we basically have a set of effects, and the instruction model is a program that can generate those effects, and then the concurrency model just consumes a program that generates those effects to produce an actual machine model. So those effects are quite basic. It's reading and writing register, reading and writing memory with all of the different kinds of memory accesses you can do, and then you have all the usual barrier, cache invalidation, taking exception, returning from exception. And then there is a few non-architectural effects of just doing the determinism and failing, which means undefined behavior. So that's an important part of this project, is correctly handling undefined behavior. So any instruction model needs to be able to fail at any point because some of its assumptions weren't made, and then the concurrency model needs to handle that properly. So more practically, with an example, here is a Coq definition that looks-ish like the real one, but not really, for a bunch of those effects. So, for example, here, reading a register, you take a register as an input, and then you have a continuation that takes the return register value that you got from that register and continues execution. So that's really like I3 style or free monad over a set of effects style structure, except it is inductive because all instruction terminates. And so similarly for all the other, like writing memory, you take the size, you take the address, you take the access type, you take the value to write, and then it returns unit, and then from that unit you continue the rest of your instruction execution. So in practice, if you take a simple instruction like load x0, load from x0 and write it into x1, you can generate from it the very simplified pseudocode compared to the actual one, which is just read R0 into an address, then read memory of that address, and write that value into R1. And if you transform that into this monadic style, you can write it with those effects. So you issue the effect read register R0, and then you put a continuation that takes the returning address from that, and then this continuation issue the effect read mem of size 8 at address of access type explicit access, and then you get the value in another continuation that will then write the register R1 with that value, and then the last continuation does nothing, just takes unit and return unit, because there is nothing to do after that register write. So the idea being that inside this continuation you can shallowly embed arbitrary complexity that has nothing to do with the concurrency model, like arithmetic, control flow, and whatever. And the only thing that you really have to reason about are those effects. So if we want to run such an instruction against a very naive concurrency model, which is just a single-threaded sequential model, what it looks like is that you will issue the register read R0, and then the naive model will take that and handle it as an effect handler and return the value 42 because that's what it has in its R0. And then you issue another effect, read memory of size, oh yeah, I put 1, I should have put 8, whatever, of this address with explicit type, and then your naive sequential model can just give the value at that address. It's simple in this case. And then you issue the write register, and then you get units, which means you acknowledge that the write has happened, which when you start going into concurrent settings starts being important. So yes, quite basic, but this handler can be much more complicated than just handling effects one after another, obviously. So that's for the basic user mode stuff. If you start thinking about more systemy stuff, you start thinking about, for example, instruction fetching. And here it's a bit more interesting. So the important point is that thinking about instruction fetching allows us to realize that actually we don't want one value of the instruction model per instruction. We just want a single one that contains all the fetch, decode, execute loop. So with a single value that does a dispatch, we can get all possible instructions. So for example, so all instructions will start by reading the PC register, getting the value, then issuing a knife fetch reads to get the opcode, and then doing a big match on the opcode. So I mean, for fixed size instruction architecture, it's just read for x86. The code here would be slightly more subtle, but I haven't thought about that too much. And then this match can dispatch. So for example, if you have an add, then inside the continuation that contains a match, you have a control flow to the add, and if the opcode matches this add, then you will run the rest of this code, like read the to register and then write the sum. And here the sum is a shallow embedding, so it's literally a Coq plus. You don't really have to think much about it. And on the other hand, if it's, for example, a TLBI, which is a system instruction, it's still relatively simple. You still read the register. Oh, I should have read R3, not R1, sorry. And then you can, in a shallow embedding manner, decompose that value into the different fields because the architecture defines multiple fields for that value, and then call a TLB effect with, and then inside that effect you can have a complicated data structure describing the system operation. So here it's a TLBI of type VA E1 IS with those two parameters, and it returns unit. So you can do quite complicated things while still hiding all of this inside the Coq function because it's a shallow embedding, so you can avoid thinking too much about the insides here. So yes, if you go to the virtual memory system, then it kind of goes mad in terms of number of events, and that's what Ben showed last time. But it's still manageable, and you can process them in order and whatever. So here we need to start thinking about the limits of how we can use this to actually produce machine models. And one of the big thing we need to think about is what an architectural model actually is. And here it's a bit iffy. I mean, there are some things that are obviously in, like registers and memory and tags, but technically non-coherent caches, you could think about them about an architectural state because, I mean, you can observe what they happen, like you can observe that this cache has an entry that is not consistent with memory. And so when you start thinking about initial and final state, you could also think about state, starting in a state that already has incoherent caches. We mostly don't do that, but we could. So here there is a bit of boundary that is like blurry. And then there is obviously microarchitectural state like pipeline, register files, coherent caches, and all that we don't want to have to care about. And so to define a machine model, the current scheme is to just take a termination condition, so like take an AND. And this sounds very artificial because it's not what an actual CPE does, but it's a fiction that we all use. And when you actually formalize it, you really have to think in terms of it's a fiction, but we all use it, so we keep doing it, of having an end of program for each PC. And then an architectural state is if you imagine an observer that after all this PC just stops the world for all threads and then observes the architectural state, and then you can start describing again an architectural state, because none of the microarchitectural state from the initial state to the final state can be directly matched back to an architectural state. So, I mean, most microarchitectural states can be refined back into an architectural state. So you kind of have to mess around to make that work. And so after reaching such a termination condition, synchronizing, flushing everything, you can have a microarchitectural state that looks like an architectural state and start saying again things about it. So the formalism is in the end quite basic if you think about, after thinking about all those caveats of just taking initial state and having a set of possible final states satisfying the formalization condition, and this is all you get for now. You also possibly for initial state can get error or special architecture constraint unpredictable behavior, which you need to handle separately. And so this framework does not support non-terminating execution. It's kind of a partial correctness. It's like if you start from this initial state and you reach this final state, then this is what you can observe. If you don't reach that final state, the model doesn't say anything about what could happen. Your computer could just catch fire. We don't care. And for now, I don't support any non-final state observable behavior. So like you could have MMIO and interact with the device, and that is also outside of the CPU architectural observable behavior, but I don't support this yet. So why we support only finite execution? So I mean, good reason is so far we don't really have good model for infinite execution. I mean, it's work in progress. And second is that if we want executability, then obviously we can't define termination, compute about non-termination and all that.
We should.
We should.
It is wonky.
Yes, this whole setup is wonky, but that is the current setup. So that's one way to define an architectural model, but if we go a bit more in depth, people would prefer to think about execution traces and witness. So I have a formal definition of what that is in my current framework. So it looks as the usual. You have your initial state, which is defined in very architecturally in terms of just register and memory. And then for each instruction, you have a trace. So for example, if you have 4 instructions, each instruction contains a trace of all the effects that have happened. So, and like it's well defined that the instruction 1 is this list of effects. Then you have instructions 2 containing this list of effects. And then you can go back to the usual arrows of saying that this write memory has been read by this read memory and putting arrow between those events. And then some arrow people are less used to about this register reading from this register writes, which is similar kind of arrow, except it's always in the same thread, of course. And then from the base relation, as usual, you can define more compose relation, like the usual from read, that says that this read missed this write and read from before, I mean, from initial memory here. So that's why it looks like. It doesn't look that much different from how people usually phrase it. The details are much more precise, especially about register accesses. And like things like address and data dependency are definitely not primitive constructs. You have to build them up from this. And so to define an axiomatic model from those things, you need to define a classifier that takes those objects, those traces, and tell you if they are valid, if they are invalid, or also if they are unsupported, which means they are consistent, but they do stuff that your model doesn't support. And then you have those special outcomes like constraint and predictable from the architecture, so you can tell this execution will trigger this constraint and predictable behavior, and therefore the set of behavior you could observe is quite large. This setup does not require any concept of candidate execution generation. So the definition of allowed final behavior is if there exists a candidate and it's accepted by the classifier, it's final state. There is no pre-step of generating a candidate execution. You have to think about all the possible candidate execution that could fit the set of constraints. Another obvious constraint that I forgot to mention is that individually each instruction must match your instruction model. So each of the 4 little boxes needs to match your instruction model. And so to define a regular axiomatic model, you just do your usual relational algebra over this witness, and then you have a bunch of side conditions, like all the little boxes satisfy the instruction model and a bunch of well-formness properties, and any candidate that satisfies those constraints is valid, and you need to consider that as an allowed final behavior. I mean, you can also hack back operational model into that by having them try to generate a trace that matches a specific execution witness. But more generally, if you want to define operational model with this framework, it's relatively easy. I mean, you can do it with a combination of just doing a regular effect handler interpreter and some state non-determinism monad, like you would do in a, I don't know, in a camel or something. And then you can, if that's not good enough, you can drop back to a state transition system that manipulates those effects more directly. So, I mean, I can show you more concretely what it looks like if you want. I mean, if people are interested. Yes, Sean is interested. So if I go on the RMM website, no, that's not the RMM website. That's the RMM website. So if you take a litmus test from ARM, yes, this is a good litmus test for ARM, and you hide a bunch of transitions, then you can start having a framework that looks like what I'm doing in Coq. So here, basically, the idea is that you already have your 4 instructions in the pipeline. So I've skipped instruction fetching for now. And operationally, you really think of it as doing all at once non-deterministically. You handle an effect of an instruction or an effect of another, and then you update your state with that. And so it's really exactly the same effect as the one I've described. Like you can read a register, then oh, I forgot to. So there are a bunch of registers that are not really registers that I forgot to. Yes. So that's read memory, and then that's a register write, for example. And you can do them all in arbitrary orders, and it will give you a result at some point. I'm just randomly clicking at this state to illustrate the non-determinism. And at some point, it will give you one possible behavior once you have just finished all instruction. Whether this behavior is interesting or not, I don't know. But like really thinking of those operational model as just randomly executing effects from all those traces in any order. And in some sense, it is a bit of an interleaving semantics, but at the level of those effects, not at the level of your original instruction. Yes?
You're using a monad to capture the ASL or the ISA semantics, but monads usually don't provide, there's a next thing to do in monads, right? Monads are based on a sequencing operation. Is there a way to capture like possible next things to do?
So, I mean, here, if I would do it now, I would probably not do it directly with the monads, but with a more basic state transition system that just, you have your instruction monad, but then your actual model is defined with a state transition system that just works. So if you imagine your state of your model contains this pipeline with value of the instruction monads for each instruction, and then each one of the value has a shape of the next effect to do is that, and the continuation is this. And then when you want to transition one random instruction in the pipeline, you take the next effect, you run it, then you evaluate the continuation and the result, and then you replace in your state the previous value of the monad by the resulting value of that continuation that will give you the next effect to run. And then you leave it there, and then you schedule again another instruction to make one step. And you can do that with the state transition system. But later,
maybe one point is, the monad is just inside a single instruction. So there's no sequencing between one instruction and the next.
Then I'm wondering,
Monad.
is that valid? Are there places where an instruction may evaluate A or B first? And that's
yes, that's
infra-instruction.
10 slides later-ish. Maybe only 6.
You'll have all the spicy details that you've dreamt of and more.
So yes, but if we forget about that, for simple instruction, it kind of looks like that. So yeah, if you want to think about not microarchitectural model, but promising, you have something that looks more like this. It's really sorry. So I mean, I draw it as a graph, but it's just a representation of all the different possible transitions you could do in a promising model. And like, like the two main transitions you can do is run a single instruction. If you know a promising model, it's either you run an entire instruction, so not step by step, like it's at instruction granularity, or you take a promise. And so the way you encode this, you run a single instruction, is that you directly interpret the whole of the instruction with an effect handler. So you take your initial state, and in that state monad, you just run all the effect of the instruction after another until you reach a new state, and that's a single transition of your state transition model. If that computation fails somewhere, then you take the bottom transition that just directly goes to an error, and if it produces a new state, then that's a single step of your model. And the other style of step that are much simpler is just add a promise to memory. So that's how promising style model work. And on that note, I have a very work in progress VMSA promising model to try to emulate / fix up the existing ESOP22 virtual memory model from them that I can talk about if people are interested. So an important point is why do we want all those different styles of model? Why not just axiomatic model? And the main reason is that if you write axiomatic model, and by write I mean like actually try to model new bits of the architecture using axiomatic model, it's very, very easy to be too relaxed because you need to constrain everything, and if you forget one constraint, you will be too relaxed by default. And so it's easy to allow really weird and nonsensical behaviors. And so using operational model is a good way to compensate that effect, because operational model tends to be too strict by default. Like you need to add new gadgets to your operational model to allow more relaxedness, to manually deorder things that you would naturally operationally order. And so if you manage to write model in both sides and make them matched up, then you have a much more confidence you've hit a good sweet middle spot. And so here are some examples of bugs we found while I tried to do that. So for example, ARM has made this official axiomatic model that is on the herd repo, and it contains mixed size behavior. And when looking at it, and that
you need to say what mixed size behavior is.
Oh yes. So mixed size, a good point. Mixed size is when you do read and write of different sizes to the same location. So most regular memory model, and including mostly programming language level models, are mostly concerned about ordering like all accesses of the same size. And like when you're in C and you have an atomic of a specific type, you will always access this memory location at the same size. But if you're in assembly, you can arbitrarily decide to do random accesses of different sizes to the main area, to the same area of memory. And things start to get tricky really fast when you do that. So that's what mixed size models are for. Yeah.
One question. So, so for this mixed size bug, was it the bug in the axiomatic model or in the operation?
So in the end, both, in the sense that there were two main So I mean, I took a Luc-Mélanger test suite of differences between the axiomatic model and the flat model, and I condensed it up into two interesting behaviors. And after talking with the architect, one of them was okay, and so the flat model needed to be relaxed, and one of them was really bad, and the axiomatic model needs to be strengthened. So in some sense, both models are wrong, I mean, I don't think we could retroactively say they are wrong because at least one of them was something that the architect kind of decided on the fly.
This is definitely a visit to the sausage factory. One sees architecture invented. I mean, it took several rounds of discussion over, with quite long gaps in between, to come to a clear resolution.
Yes, and I think we have now reached a resolution where we can, I mean, I haven't done it yet, but we can make all the model match up and agree.
I would like to see a V600.
And part of the resolution was that the architects forbid some behavior that earlier used to be allowed.
But
Quite unusual.
behavior which only exceedingly implausible imaginary hardware
Yeah.
was thought to conceivably exist.
So yeah, the axiomatic model naively allowed it.
It's not sufficiently bad from a hardware implementer point of view.
Yeah, but this time it was enough. So yeah, axiomatic model allowed the weird behavior, and to find the microarchitectural explanation was really mad. I mean, the microarchitectural explanation we found was really mad and involved things that no sane hardware would ever want to do, and that was enough to convince the architect to forbid it.
In the end, right, it's the architect's job to make this trade-off between how usable the thing should be versus how much they want to allow.
I understand. I'm impressed that there's one more example of this class, and
Yeah.
I'd like to see that example.
And
The class where hardware folks say that we are not going to do that.
yeah, and I mean, yeah, this specific behavior, I mean, I can talk a bit more later, but this specific behavior was really bad because it forced operational model like flat to remember for all bytes the footprint of the write that wrote that byte all the time, and that's not something most hardware does, but to allow this, you needed that extra information, which was a quite drastic change. So yes, that's one of the things we found by trying to reapproach existing things on the operational side. And then, sorry, you have a question?
Is the axiomatic model, presumably it's not executable, isn't it?
So, I mean, my formalization, not yet. The existing tools like HERD or ILAN make them executable by going through this phase of candidate execution generation where they know enough about what the axiomatic model looked like on a single thread to generate thread traces, and then the number of interconnection of read and writes to enumerate isn't that large, and so you can do all of them. But there is no proof that this pile of hack is sounds compared to a baseline definition that doesn't have those steps.
So do you prove any formal relationship between the axiomatic and the operation?
So far I want to, but I haven't. But it is perfectly doable, and that's the plan.
A paper proof the equivalence between the operation and axiomatic. Hopefully one of the things this work will enable us to do is to write that down. Looks nice.
Christopher Pulser's PhD thesis was a paper proof for the axiomatic operational correspondence for the ARM model as it was then. But apart from that, we more or less have experimental testing comparisons, big sweeps of litmus tests.
Yeah. So there is a proof of equivalence, formalized proof of equivalence with the promising model, but it's based on a toy assembly language, not on the real assembly or an interface like that. And so the amounts of extra problems that could come up from that is not really known. But yeah, hopefully this framework will allow us to do most of those proofs properly. So my current status, which doesn't include any proof, is have this framework in Coq with only ARM-A support for now, and have proper definition of what a machine model is, what an execution witness is. I have an ARM user mode promising model, not mixed size, so basically the same as the one that was published on Popper 19. I have two ARM axiomatic models, the user mode version and the VMSA ESOP 22 version, both not mixed size either. And then we have a third sequentially consistent model that is wrong but useful for testing and smoke proving. It's smoke testing but with proofs. And a sequential operational model that is here to illustrate how to write straightforward operational model by just interpreting all the effect trivially on a sequential flat state. So Axel, which is a program logic over a weak memory model that went out at Popper 24, uses a prototype of this framework, but we haven't rebased it on recent version. And in addition, yeah, I have lots of halfway done things. Like currently there is the interface in Coq, but the pipeline of going from Sail to that isn't fully finished. I mean, I think it's still, I'm really close on 1-2 more weeks of work, but I can't say it's finished today. And I also have this promising VMSI model that have halfway implemented in Coq, but not finished because of various blockers and plumbing problems. And executability is in theory achievable in the sense that all the Coq definitions I've written are computable according to Coq, but we haven't done a very good job of actually extracting them to OCaml and running them. So that's also in my to-do list. And then there is the two big problems that this project has made pop up, which is handling partiality of models and instruction parallelism. So I will talk a bit about that, but it's more of a taster, and if you want more details, come talk to me later. So partiality is a problem that comes when you start thinking about model inclusion and refinement instead of just model equivalence. And when you start thinking in terms of model inclusion, you need the models to correctly handle undefined behavior. And if you want to properly handle undefined behavior in an axiomatic model, you need the concept of partial execution and like execution prefixes and things like that. And we don't really know how to do that. So if you have PO union RF or PPO preserve partial or preserve program order union RF, it's relatively easy, not in the sense that it's easy, but in the sense it's already solved, and that's what tools like GenMC use. But for the ARM with load buffering, it's actually hard because PPO union RF is definitely not acyclic, even if you restrict to preserve program order. And so what I've been working on is some kind of solution that involve, in some sense, restoring the temporality of events. So instead of a read being an atomic event, you start reintroducing a beginning and an end and have some kind of order on beginnings and some kind of order on ends. So here by beginning and ends, I mean like the moment you speculate the value and the moment where you complete the effect or commit that this value is definitive. And if you start thinking about those two concepts and the interaction, you can start to reinvent an order that happens to be acyclic and has the property you want about partiality, but it is much more complicated and very much work in progress. And it's also complicated for promising models to handle undefined behavior properly. So for operational models, it's quite easy because, I mean, you do your operational model thingy, and if one instruction that is not speculative hits an error, then that's an error, period. But porting that notion back to the other kind of models is a bit complicated. I have a plan to fix up promising, but very work in progress too. And now what Grigory has for. So far I've only talked about internally sequenced instruction over a free monad, so you do the effect one after the other and you wait on the previous effect before you do the next one. And surprisingly, it's a lie. Reality is not so nice. And so my best idea to handle this is to get away of free monad and start adding more complicated constructs like async and await inside the instruction monad so that instruction monad can start issuing multiple events. So in some sense, instead of having a next event, you have a set of next events because you have, when you do an async event, it's not really an event, it's more of a control flow operation. Then the event in the main thread after the async and the first event inside the async are both good candidates for the next event and could be executed in either order.
For a bit more context, we optimistically thought, or at least I optimistically thought for a while, that we could get away with just fork join parallel is intra-instruction concurrency, and Thibaut says this turns out not to be the case.
Yes, so I can draw some little diagrams, but there are some instruction that requires more complicated structures. And actually it's even worse. Because in practice, if you start doing this distinction between speculation and completion, then you start wanting dependencies on one but not the other. So you need some kind of weak kind of await that can, at speculation time, invent the value that comes from the async block, but at commit time actually wait on it to be able to really commit the value as non-restartable. So you have this speculate, which is a weak await that will first invent the A speculatively, but then check it against the future later when you want to actually commit the instruction. And so if you heard about ARM's intrinsic order, it's the difference between the internal data and internal control. But it's not really just about data. It's mostly coming from data flow and control flow, but not completely. This interface will become much less nicer as time goes on, sadly. And so most instructions are not affected by this, and you can keep thinking about them as a linear instruction, but this is a non-exhaustive list of instructions where a thing starts to go bad. And so CAS, and in general, any read, modify, write instruction when you don't have a direct data flow between the read and the write are affected. Conditional selects and instruction with internal control flow are affected. And anything that does multiple memory accesses in parallel, so load pair, store pair, any unaligned access, and basically even any vector instruction starts being affected too. Yeah.
Specifically for read, modify, write, can you have the treat it as two different instructions and relational model?
Yes, yes, but no, because there are still a lot of interesting dependencies. So I mean, those two instructions, if you were to split it, you would still need to connect them with various things that you don't usually see between instructions. And rather than invent new fake dependencies between instructions to handle that, I prefer to do it properly and keep one instruction being one instruction, which is a very nice property.
Also, it would, I guess, interact badly with exceptions if
yes,
one instruction or multiple instructions.
Yes, because yeah, when you start having synchronous exception, like the notion of instruction boundary starts becoming very important.
Similarly, page table translations and things like that. If you're reading and writing to the same location, you don't want to do a page table walk twice.
Yes, so I mean, that's something that isn't fully resolved, but we expect you do the page table walk once, but we haven't asked the architect really that question.
It's a question whether it's permitted for hardware to do it twice. We don't require them to do it twice. Maybe they're allowed to.
Yes, so the question of whether it's required to do it once is another question. Similarly, for unaligned access, the ARM definition for unaligned access is just do a bunch of 1 byte accesses. And what's unclear is if you do one translation by page, or if you are allowed to do one translation per bytes with potentially different results. So there is a bunch of complexity that comes with all that stuff. So that's for the formalization part. And so as part of making this formalization, I also made a bunch of new models. So there is this mixed size stuff that we talked about previously, where by doing both a strengthening of the official mixed size ARM axiomatic model and a weakening of the flat model, I think we can make them match up. And I also implemented the mixed size promising. That was helpful to think about both of things and hopefully sits correctly in between and will be joined. And then, yeah, I have this virtual memory promising model that improves on various things from the ESOP22, which are mostly things that pop up when you try to operationalize an axiomatic model and you realize, oh, this is way too weak, why? And you realize it shouldn't have been that weak. And then there is also a bunch of things that come to actually thinking about registers, interaction, dependencies precisely. And in particular, I've been thinking a lot and making plans about how to integrate this peak dependency mechanism that ARM introduced into promising and flat. and how to make our handling of system registers and relaxed system registers correct. So these are all things I've worked on, and none of this is really finished or set in stone. And
all of which one needs to have a believable semantics for if you want to actually reason that systems code.
yes,
No.
yeah. And so my more long-term plans is to start. So my short-term plan is to start doing, now that I have 2 axiomatic models, start to prove a refinement to see how that goes. And then I have lots of work to do about handling partiality and parallelism for axiomatic model and promising models, and formalizing some of my existing but only on paper models, and prove some amount of the expected equivalent and refinement, but not all of them. And yeah, writing a thesis is also something on there. So the conclusion is that, yeah, formalizing all this stuff is really worthwhile and is doable, even if I've been hacking at this for 3 years now. It is happening. And yeah, some of the caveats is that, yeah, this whole setup is for hardware models only. There are really a hard-coded concept of what an instruction is, and the number of threads is really fixed and can't be changed. So it's really not suited for programming language level modeling. And I do expect that model extracted from Coq will be much lower than existing tools, but it's more about testing whether the Coq model is sensible compared to the tool and not actually using it as a tool. Although maybe that will be doable and the slowdown won't be that bad. I don't know. And yeah, Coq is not a great proof system, but we really wanted to work with Iris, so we were kind of stuck with Coq. And yes, and the last bit that is somewhat annoying is that, yeah, this set of effects in the interface is not set in stone, and there are many more effects that we need to add. And as we want to cover more part of this and that bit of the architecture, or maybe other architecture, we keep wanting to add new effects. And so there is a bit of a juggle of when to add a new effect, when to cram the semantics of a new effect inside the old effect, and it's a bit of some kind of basic API question of how to encode the set of possible effects into a reasonable shape and reasonably understandable set of effects with parameters. Because you could always split an effect into 2 or merge 2 effects in an effect with a Boolean parameter, or there are arbitrary things you can do on your Surface API, and what things are good to do are often only known after the fact. So yeah, thank you for your attention. If you have more questions, I'm happy to talk about this offline, or not now.
So last week, I think Dominic Reis talked about these universal contract things.
Yeah.
And in particular, I guess you could try to use that to capture the effect of constrained unpredictable behavior at a given exception level.
Yeah.
Have you thought about phrasing that in terms of the sort of like a set of effects or a constraint on the effects?
Not really. So my main point was to correctly flag the constraint unpredictable, so have a partial execution that says, hey, you've triggered it. But I've not thought that much about how to go from that to a well-defined set of final states. Because when you have a regular execution that goes to the end, then you have basically one single final state it corresponds to. Whereas if you have a partial execution that reaches a constraint unpredictable, then there is a second step of going from that to a large set of final states you could have observed. I don't really have a good ideas or plans on how to do that, but it doesn't, it sounds doable, and you need to start splitting your architectural state into what can or can't be touched by the set of instruction, and then with those universal constructs you can prove that the set of final state is defined by having those bits stay the same and those bits change to arbitrary value.
I was thinking of a more sort of, like a sort of, not really a result, but you take your architectural state and you say, well, it's this state, except you can apply any combination of all those effects rather than any combination of all those bits of instructions. And then it wouldn't help you compute the result, but it would help you at least characterize it.
I mean, applying an individual instruction effect to an architectural state is very iffy at best.
But you have your monad of effects, so maybe you could try.
Yeah, but what I'm saying is that, I mean, in those models, like, I fake up having an initial and final architectural state, which is already not really true. And I try to avoid as much as I can the concept of architectural state in the middle, because that would be even less true. And so I'm really worried about reintroducing that concept in the middle to support that. Any other questions? No.
So what's the big theorem you're trying to prove?
So, I mean, there isn't one big theorem. It's more of, I mean, in an ideal world with infinite time, I would like to have all the models we have already defined, and whenever we think there should be an inclusion or an equivalence, prove it. But it's more of a category of zoology categorization of model than a single big theorem. So I mean, right now I'm working on proving a refinement between a user mode model and a virtual memory model, which means that if you have a virtual memory model but you don't actually change the page table, it collapses down to a user mode model. And that's one of the theorems I'd like to prove, but the goal is more to have a framework to efficiently prove those properties rather than prove a precise one. And also, I mean, that's my personal goal, but the goal is also that this framework can be used by other people to define program logic or prove refinement with higher level abstractions, like the simplified model that we have to detect break before make failures or various other things like that. Just be a baseline semantic for anybody that wants to reason about the architecture.